Okay, so problem 2 is a little bit more complicated than problem 1, mainly because you have both a hinge here and you have this T shape here, right? This little outcrop here. I'm going to go over how to deal with the hinge and a little bit on how to deal with this outcrop here. Basically, for this little section, this is what we would consider this to be a frame, even though it's not really framing anything in particular. From E to C, whatever axial forces you have in here will become flipped. Your axial forces in this member will affect your shear forces in the perpendicular members. Likewise, whatever shear forces you have in here will affect the axial forces in this member. And we'll be going over that a little bit more detail later, but that's just a first heads up. For this problem, you have 4 reactions. The easiest way of dealing with these 4 reactions, or the best way, that you need a fourth equation essentially, and the equation is going to come from this hinge here. So if I look at that hinge, so normally I have 3 global equations, right? I have sum of fx equals the sum of f in the y direction equals the moment about a point equals 0. In this case, I also have the moment about the hinge, and for this one I'm only looking at one side, but the moment about the hinge must equal 0. In other words, if I'm at the hinge and I look to the left, the sum of all the moments about B on this side must equal to 0, and the sum of all the moments about B on the right-hand side must also equal to 0. So how does this actually work in practice? I'm going to draw my member here. So let's draw AB first. So I have my hinge here, right? This is B. I'm doing moment about B equals 0. And I'm going to say that clockwise or counterclockwise is positive. If I do that, I'm going to get, so this is AY. I'm going to get a W times L times L2, right? This is height W times length L, acting at, that's the total load. The load acts at a distance L on 2, and this is length L, minus AY times L equals 0. Therefore, the AY is equal to WL on 2. And that is my first reaction. So I could have looked at the other side, but the other side has 2 reactions, so I have 2 unknowns. By looking at just the left-hand side, I'm able to get this unknown right away. So that's the main reason why I looked at the left-hand side. Now, if I'm looking for the difference between moment about the hinge and moment about Z, is that moment about the hinge, I'm only looking at one side or the other. If I want to do moment about some point, for example, let's do moment about D, I would have a much more complicated moment diagram, or moment equation. So for example, let's do moment Z at D. So I'm going to look at, say, the moment about D must equal to 0. And if I'm doing this, I have to look at every force, both on both sides of the hinges. And it's still doable, but as you'll see, this equation is much longer. So if I do moment about D, and I'm doing it the counterclockwise direction again, I have negative AY times 2.5 L plus W times 1.5 L times 1.5 divided by 2 times L plus L minus WL times L on 2 plus WL times L on 2 minus CY times L equals 0. And so, like, it's not a particularly hard equation, but it's just there's a lot more terms, there's a lot more signs you have to keep track of, there's a lot more room for error, and you want to minimize your chance for error. If I were to actually solve this, and this is the way you can check your work later, I should get that CY is equal to L on 8 WL. So those are 2 reactions. I'll let you solve for the last 2. As I mentioned earlier, dealing with that corner is a little bit trickier, but essentially your axial forces becomes your shear forces. And what do I mean by that? Let's look at this in close up. I was trying to get rid of that little stem there, but So I have some force P, right? That's acting here. In this member, P is causing shear, right? Let's pretend that I have reactions. Let's pretend that I have a pin and a roller. In here, P is causing shear. If I were to draw this, there's no axial force in this member. So if I were to draw, let's call this A, B, C, and D. If I were to draw the axial force diagram for BD, it would just be 0. There's nothing there. The shear diagram, however, if I were to draw it, would be something like this. Right? I have shear in here, and we can argue about the sign convention later, but I do have some value for shear in here. When I'm looking at A, B, C, however, that force is going to cause an axial force in number AB. So when I'm looking at AB, why did I get rid of that? If I'm looking at AB, this is A, B, C, this is axial. I'm going to have some reaction this way, negative P. And this is going, or sorry, a P this way. I shouldn't use a negative sign there. P that way. And this is going to give me some tensile force in AB. So I'm going to have an axial force diagram that looks like this. So even though my axial force, even though it's acting out here, I actually develop an axial force in AB. One way of thinking about this is that, well, what if I just draw it like this? What if I just draw my diagram like this? That is fine. You can do this as well. Just make sure that you remember to draw diagrams for BD as well. Essentially, all I did here was I moved this load down to this point and added an extra moment. These two things are equivalent. But I find it easier to just leave it like this for now, personally. When I'm drawing diagrams for these problems, you should draw them on your diagram, on your problem itself. So for example, the problem was drawn like this. You should draw this out and then draw your diagrams directly on here. So we were saying that the axial force is going to be like this, right? This is your axial force diagram. You're going to do the same thing for your moment and shear diagram. So for example, you'll say that your shear diagram, you'll say that this is positive, so you'll get something that looks like this for your shear diagram. And then for your moment your shear diagram will also have some value up here. So in order to distinguish this, like, do you guys see what I'm saying here? Like this is my axis and shear. This is my axis and shear. So instead of drawing a diagram for this length and a diagram for this length, I'm drawing everything on the same diagram. This is kind of like how SAP would present it if you were to do results. Like how SAP presented your truss results, it showed everything on the same diagram and just had all the diagrams at different angles. And I'll do the same thing for my moment diagram. Okay. The last thing I want to note is when you're drawing your deflected shape, just keep in mind that when you have members that meet like this will always be a right angle. This is what we call a frame. We're going to assume that your frame will always obey this right angle. So you might have a deflected shape that looks something, let's say the original shape was this. Your deflected shape might be like this. But this is still a right angle at this little joint right here. Okay, with that, I think that's everything for this problem. Let us know if you have any other questions.